So our next speaker is Qinggang Gao from the University of Melbourne. Have we got a speaker? Yes. Okay, sorry. So towards enhancing climate projections through improved understanding and simulations of marine low clouds. Do we need to swap the... Okay, we've got it. Oh, you've got 12 minutes and I'll give you a warning when there's 2 minutes left.
Okay, thank you. Okay, good morning, everyone. I'm Qinggang, and I'm a postdoc at the University of Melbourne working with Yi. Here I'm going to talk about improved climate projections through better simulations of marine low clouds. So I know most of you are interested in oceanography or high-impact weather, but I have to say that no clouds, even is not very attractive scientifically for many people, but it's very important for climate projections. It needs to know one of the largest uncertainties in climate projections. Even in a single SSP scenario, because of these clouds, it's unclear how warm the climate will be. And the assessment of equilibrium climate sensitivity in IPCC-AR6 is not directly informed by climate models. You can guess why? It's mainly because of the clouds that is not well resolved in these models, and people think it's better not to use the model output here. And if you look at this figure here, we can see that no cloud reflectance changes is well correlated with equilibrium climate sensitivity across these models. And the difference in simulation of low clouds can lead to a very large difference in equilibrium climate sensitivity. So regarding the current research status, the cloud evolution mechanisms are relatively well understood in terms of the dynamics, but much less is understood about precipitation, drizzle, aerosols, and mixed phase clouds. So because predicting clouds is so difficult, some cloud controlling factors like sea surface temperature are used to inform climate changes based on their statistical relationships with cloud cover and so on. So when we talk about low clouds, it's mainly stratocumulus and stratocumulus. And observations have shown that stratocumulus may have a weak feedback in the future, but greenhouse warming may induce stratocumulus breakup. When the stratocumulus stacks break up, it will reflect much less sunshine, so it leads to a very strong positive feedback. So many people have seen kilometer-scale climate projections may become feasible in next decades, but our research question is, can kilometer-scale climate simulations capture these low-level clouds? So here I use a range of satellite and modeling products. I use series in the top of atmosphere radiation fluxes and liquid water paths retrieved from both polar and geostationary satellite. And I also use Himawari. It provides a product of cloud type classification. So it's geostationary satellite with 5 kilometer horizontal grid spacing and 10 meter temporal resolution. So I also use CloudSight data set. It's a polar orbiting satellite. It is equipped with cloud profiling radar and can retrieve cloud droplet number concentration. I will demonstrate how important this number is. So I also use cloud droplet number concentration from CMSAF. It's a product from Europe, and the liquid water pass from Moody's Aqua product. So modeling products, I mainly use ERA5 and Barra R2, both are reanalysis products. Barra C2 is downscaled from Barra R2 with reinitialization every 6 hours. And Barra C is downscaled from ERA5, so it's a free running simulation. This table indicates the differences between Barra R2 and C2. This is going to be the main focus of this study because I'm a modeler. So let's focus on Barra C2. It's 4.4 kilometer grid spacing and has 17 levels up to 40 kilometers. It uses a regional atmosphere and land configuration from the mid office. It's called RAL 3.2. And the main parameterization mechanisms are quite different from Barra R2. It includes the boundary layer parameterization, convection, cloud scheme, and cloud microphysics. the radiation scheme are the same. And just to mention that BaraC2 use a new multi-moment bulk scheme CASIM, but because the double moment macrophysics does not work very well, so now we are still using a fixed cloud number. So I also use ACCESS-ROM3 regional atmospheric model. It's implementation of the mid-office unified model with RAL 3.2. So we run a control simulation like BaraC2 for a case study because we can only afford that. And also, it is nested within a simulation like BaraR2, which is driven by ORNI ERA 5 data, so we can do a direct comparison, make it as close as possible. We perform 22 sensitivity tests, and 6 are shown here. The SA indicates Southern Australia. We use different horizontal grid spacing to check the resolution dependence of the modeling results, refining the grid spacing from 4.4 to 1.1 kilometer. And we also run 2 simulations by reducing the cloud number to 100 to 50 per cubic meter. And in the last simulation, we combine the benefit of higher horizontal resolution, 1.1 kilometer, and cloud droplet number 50. So firstly, let's look at the comparison of these modeling products with observations in the series. So here in this figure, we show the outgoing shortwave radiation. We only show statistical significant differences, and the root mean squared difference and the mean difference are area weighted and shown here. Positive radiation means downward, negative upward. So the key message here is that BaraC2 reflects too much shortwave radiation compared to series due to cloud radiative effects. And the bias in BaraC2 exists in all years, all months, and all daytime hours, so it's consistently overestimation. The bias also exists in BAPA-C, so even with a different model experiment design without reinitialization, there is also bias. And it also exists in our RAL 3.3 in the latest configuration, so we can see it's not yet resolved by the latest development. This figure compares the low cloud cover with the Himawari dataset. It's important to note that the definitions of low cloud cover are different across these modeling products and Himawari. Himawari uses a cloud top pressure threshold of 680 hectopascal, where the other modeling products use a pressure threshold of around 800 hectopascal. And the Himawari uses a binary classification. It's either low clouds or something else. And the cloud overlap can be very tricky, especially for Himawari, because it cannot penetrate high or middle clouds. But still, through this comparison, we can see that BaraC2 overestimates the low cloud cover compared to all other products. And we also found that this overestimate is consistent through all years, months, and hours. And the bias also exists in BAPA-C and RAL 3.3. So this is a comparison for liquid water pass. Series also have a product of liquid water pass. I don't know how reliable is that, but I just show it. I will check later how reliable it is. Again, we see BaraC2 overestimates the liquid water pass. So it will, a larger liquid water pass will lead to larger optical depths, so makes the cloud more reflective. So it seems to suggest that BaraC2 is more simulates too much and too reflective low clouds. And you may know that in CMAP6 models, the models normally simulate too few and too reflective clouds. But here is more consistent. So we choose a case study to investigate the individual processes. We choose this 1st to 2nd of June 2020, because there are widespread low clouds over the Southern Australia. So first step is to reproduce the bias using the control simulation, so we can confirm that it is a problem with the model and with the parameterization rather than some experiment design with BARA-C2. And question, could the bias be reduced with higher horizontal resolution? This is the first thing I check. And when we increase the horizontal resolution to 1.1 kilometer, we can effectively reduce the root mean square difference by 23 watt per square meter. And the magnitude of mean difference is also reduced by 34 watt per square meter. I'm not yet really sure when there is such a resolution dependence of the modeling results, but a hypothesis is that some of the parameterization schemes are tuned for 1.1 kilometer. So it is reasonable. It does not work well for 4.4 kilometer. So when we look at cloud droplet number concentration, I corrected some observations to see if they are what's the magnitude. So for CM-SAF annual mean across the globe is 92.2 per cubic centimeter averaged over the globe, but much smaller over Australia and the surrounding ocean. And you can also see there's a large land and ocean contrast. And we have also a cloud set overpass over northeast Australia around Great Barrier Reef. We also found that cloud droplet number concentration is lower in this product. So it motivates us to reduce the current default cloud droplet number concentration in the model from 150 to something lower, like 50. So we also find that reducing the cloud number can improve the modeling results. It makes the cloud much less reflective and also have an impact on the low cloud cover. So next slide shows if the higher horizontal resolution and the reduced cloud number can accumulate, the effect can accumulate. So we can see that the root mean square difference can be reduced to 53.8 watt per square meter, and the mean difference is reduced to 0.6 watt per square meter. And it even shows a better performance than ERA 5. Also, ERA 5 is not very good in no clouds. I think there's no clouds in ERA 5. They're just the radiation broken blocks. So in this simulation, we also checked the liquid water path. And we also find that in this higher horizontal resolution simulation, the liquid water path is more akin to MODIS retrieval of cloud water path. So here is a summary. So BARA-C2 overestimates outgoing shortwave radiation, no cloud cover, and liquid water path over ocean compared to satellite products. The bias also exists in BAPA-C, RAL 3.3, and RAL 2M. The bias could be reduced by increasing horizontal resolution and decreasing cloud droplet number concentration. So I think I would really want to discuss some aspects here. So as you can see, our goal is not to tune the model to match the observations as close as possible. Otherwise, we will use another different cloud number to reduce the bias more. So I think the point is we identified there are some processes leading to the bias, and we want to represent these individual processes better. So as a fixed value of cloud number is hardly sufficient across different regions, across different time, I think our next step is to prognose cloud droplet number using cloud aerosol microphysics interactions. And also sub-kilometer scale simulations may be required to investigate the resolution dependence of the modeling results. Thank you.
Thank you. We have time for one question. Yes?
Thank you. Did you have a look at what the impact on precipitation was with the changes in the cloud droplet number?
Yes, I checked both the climatological precipitation and also for the case study. For the climatological precipitation, there isn't much difference as far as I remember. And for the case study here, there's no much precipitation. So for this case study, I wasn't worried about precipitation.
Okay, thank you. We'll move on from there.